project is going to take us into the area of reasoning. There are two basic types of reasoning. Today we're going to talk about inductive reasoning. Tomorrow we'll talk a little more about deductive reasoning. So inductive reasoning. An inductive reasoning is basically observe and make a prediction based on what you've observed. A lot of the scientific method is based on inductive reasoning. It's a perfectly good way to reason. There's nothing wrong with it. But we have to remember that the conclusions we make are what are called conjectures, or basically guesses, based upon what we've observed. The conjecture, like I say, fancy word for a guess based on observation. That's what's going on here. So a lot of times we see this sort of thing on IQ tests or other type of things where they show us a pattern and ask us what comes next in the pattern. And this is an example of inductive reasoning. Here I see figure 1 is a circle with two sections, first section or top section shaded. Figure 2 has 4 sections. Figure 3 has 6 sections. What do you think the fourth one would look like? Well, probably going to be a circle. Oh, that got a little bit bigger than I wanted. Let me see if I can move that. Come here. There we go. And how many sections is that circle going to have? Well, I'm guessing probably going to have, what do you think? 8 sections. First one had 2, next one had 4, next one had 6. It's probably going to have 8. We're probably not going to be perfect here when we draw this, but we just have to accept that we don't have to be perfect all the time. Just get the basic idea. So I've got my 8 sections. Which section is going to be shaded? Well, in every one, shading started at kind of this 9 o'clock area right here, and then went around to wherever the next line was. So I'm going to shade here and take it to the next line. So my shading is going to be there. And we've just used inductive reasoning. This solution is my conjecture about what comes next. That's inductive reasoning. What would the fifth figure be in that pattern? Well, the fifth figure would have to have, again, a circle. If we continued, and how many sections? Well, in this case, we'd probably have to have, we went 2, 4, 6, 8. So my conjecture is going to say there are going to be 10 sections. This is going to get a little tricky. I'm not quite sure how this is going to look, but I'm going to do my best. I can already tell her off. That's okay. We'll make the best of it. Guess what? My picture isn't beautiful. Oh well. You'll learn very quickly I'm not an artist. And shade that one. And again, I'm not judging you on questions like this, especially on quizzes and tests, on your artistic ability. Do you have the general idea? Are you able to demonstrate what's going on here? Here, 5-pointed stars. What's going on? Well, basic 5-pointed star, the center is dark and a little bit lighter shaded on all the outside except this one right here. Second pattern, same picture. Oh, now 2 are unshaded. Now 3 are unshaded. So guess what's going to happen next? Well, I'm going to draw our 5-pointed star. Dark shading in the center. And light shading in how many sections? Now probably just this one. I'm just going to indicate that with some lighter shading. Or gosh, I've got 1 circle, then 3 circles arranged in a triangle, then 6 circles arranged in a triangle. What am I doing? I'm adding a row each time. So my next one is probably going to be 4 circles, 3 circles, 2 circles, 1 circle. And if we wanted to go to the 5th number in that, we'd probably add 5 circles along the bottom. You get the idea. Inductive reasoning. We're looking for a pattern, and we're expounding on it. There are also patterns in numbers and in mathematics. Numbers such as 3, 4, and 5 are called consecutive integers. Integers, you'll recall, are whole numbers, positive or negative. Consecutive means they come in a row. So 3, 4, and 5 would be consecutive. 8, 9, and 10 would be consecutive. 12, 13, and 14, 100, 101, 102. Any three numbers in a row are consecutive integers. Even -9, -8, -7. Those would be consecutive integers. All right? No skipping. Consecutive. Make and test a conjecture about the sum of any three consecutive integers. The sum of three consecutive integers. Well, let's start with the three easiest ones. 1, 2, and 3 are consecutive integers. If I add them up, I get 6. Okay. Let's try another one. Let's do 3, 4, and 5. 3 plus 4 plus 5. 7, that's 12. How about 9, 10, and 11? That's 30. Are you noticing a pattern evolve? Now notice, we're not just going to work from the words, we're going to actually do some numbers. In fact, if I really want to be careful about this, I might want to do 2 plus 3 plus 4 to get all of them in there. 1 plus 2 plus 3, 2 plus 3 plus 4, 2 plus 3 plus 4 is 9. 3 plus 4 plus 5, 4 plus 5 plus 6 is 15. Oh, now do I notice a pattern? Oh, I didn't mean to erase that. I'm sorry. I'll try that again. Do we notice a pattern about the sums? Well, yeah, they're going up by 3 each time, aren't they? Or, and this is a little tricky, but I'm going to point this out to you. Notice the relationship between this and that. Oh yeah, the sum is always 3 times the middle number. So that might be my conjecture. The sum equals 3 times the middle number. Now I know it's kind of tough. How in the world are you going to notice that? Well, practice. You're going to see problems like this. You're going to see them over and over again, and you're going to start looking for things like that. You're going to start looking for patterns in practice. There are a lot of things that are a little tricky here. Counterexample we've already talked about. A counterexample is an example that proves a conjecture false or proves a statement false. So counterexamples prove that inductive reasoning is false, because I can make whatever conjecture I want. Doesn't necessarily mean it's true. For example, I can make this conjecture. The sum of two numbers is always more than the greater number. That's a conjecture I could make. And if I base that on a few observations, let's say I had some observations, say 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5. Yeah, the sum is always greater than, it looks like that's true. The sum is always greater than the larger of the two numbers being added. But it's not true. How can I prove that that's false? What's a way that I could prove that's false? What's a counterexample? And this is something, again, that creatively you need to come up with. Now, a few hints for you. When I'm looking for counterexamples, generally numbers I'm going to look for counterexamples are, what happens when I throw 0 in there? 0 is a good number for counterexamples. If 0 doesn't work, does -1 make a difference for me? If -1 doesn't work, does 1 make a difference for me? And if all those still work, try a fraction. Try 1/2 or -1/2. Usually if we're going to find a counterexample, it's going to be amongst those particular numbers. So let's throw something in there. Let's throw a 0 in there. 2 plus 0 equals 2. Is the sum greater than the larger integer? And no, it's not. It's equal to it. It's not greater than it. So 2 plus 0 equals 2 is my counterexample. Sum is not greater than the larger integer. I could have said 2 plus -1. If one of those integers is negative, then the sum is not greater than the larger number. So that's something to keep in mind. Provide counterexamples for these. The value of x squared is always greater than the value of x. Well, again, when I look at my initial examples, I say, well, 2 squared is 4, and 3 squared is 9, and 4 squared is 16. Oh, yeah, the square is always bigger, but let's check my lovely counterexample numbers. Which one would you like to try? How about 1? Is 1 squared, 1 squared is 1. Is 1 greater than 1? Well, no, it's not. So, the value of x squared is always greater than the value of x? That's false. Here would be my counterexample. Another great counterexample for this is 1/2. 1/2 squared is 1/4. When you square a fraction between 0 and 1, the square is actually smaller than the original number. Little algebra fact, that helps you out. The sum of two numbers is always greater than their difference. Now, at this point, you've seen a couple of counterexamples. Maybe if I throw a 0 in there. 3 plus 0 equals 3. 3 minus 0 equals 3. Is the sum greater than the difference? No, it's not. Another good choice might be to throw a negative number in there. This would be a counterexample, by the way. Another counterexample might be 3 plus negative 1 is 2. 3 minus negative 1 is 4. Here's an example where the difference is greater than the sum. Just saying, there's lots of counterexamples out there. So we're going to be looking at inductive reasoning and providing counterexamples as part of our assignment today. And that's the first part of Chapter 2, Section 2. We'll get into the second part tomorrow. See you in class.